In this video, I'll show you how to solve the ALEKS problem called Understanding How Electrostatic Forces Cancel. This problem is going to give you 3 different scenarios. Each scenario is going to have 3 point charges. One of the point charges is going to be highlighted by having a little green ring around it, which is actually kind of hard to see. So I'm going to highlight it even more with this green highlighter so you can see which one we're talking about. And the question wants you to determine if there is a net force on the one particle that's been highlighted in green. If there is a net force, it wants you to decide if the net force is going to push that particle to the left or to the right. And you're going to indicate that by picking the correct little bubble associated with each scenario. So if you think that the net force is going to move the particle to the left, you'll pick this bubble. If you think it's going to be moved to the right, you'll pick this bubble. And if you think there's no net force and it's not going to move at all, you'll pick the one in the middle. So there are a couple of concepts that you want to keep in mind when you're solving this problem. First of all, opposite charges attract. So if we have particles that have opposite charges, they are attracted to each other, they move towards each other. And if we have particles that have like charges, the same type of charges, they repel each other, they move away from each other. And we're talking about opposite and like charges, we're talking about the sign. So a negative charge is attracted to a positive charge, and those two charges or those two particles are going to move towards each other because they're attracted to each other. A positive particle with another positive particle, we say that those are like charges and they repel each other, meaning that they move away from each other. The other thing that we want to keep in mind when we're working on this problem is that the closer two objects are to each other, that means that they have a greater effect or a stronger force. So objects that are close together are going to have a greater effect than objects that are far apart. And then also the greater the charge is, so if we have a large magnitude of charge, meaning that it is very negative or very positive, that is also going to have a greater effect than something with a smaller charge. So if we have two objects that are closer together, they're going to have a greater effect on each other than two objects that are far apart. If we have an object with a large magnitude of charge, it's going to have a greater effect on everything than a particle that has a smaller magnitude of charge. So let's take a look at, I think that let's do this one first. I think this one is maybe the easiest one. So we have, we're trying to think about what's going to happen specifically to this particle in the middle as it is being influenced by these 2 point charges on the left side and the right side. This, if we just focus first on the interaction between these two particles, because these are like in terms of their charge, they're both positively charged, they are going to repel each other. They're both going to move away from each other. Although at this time, we're only concerned about what's going on with this guy, so we're not going to identify the motion of this particle. So this particle over here is going to cause our highlighted particle to move to the right, to the left. And then the interaction between these two particles is basically the same. It is also a positively charged particle, so that's going to want to push it to the right. The question is now, is the force on this particle pushing to the left the same as the force which is causing the particle to be pushed to the right? Are they going to cancel each other out and result in no net movement? Is this a greater force which would cause it to move to the left, or is this one a greater force which would cause it to move to the right? That is going to be based on these variables here. First of all, let's talk about the magnitude of charge. Both of these have a magnitude of 2. So in terms of the magnitude, they are equal to each other in the effect that they would have on our highlighted point charge. So we can't use this to help us identify, or well, I guess we can. We can say that based on the magnitude of the other two charges, the force on the center charge is exactly the same to the left and to the right. The other thing that we can look at is the distance between these particles, because we have these nice little lines here to help us figure it out. This particle has 1, 2, 3, 4 units away. I'm just going to put that 4 down. The one on the right is 1, 2, 3, the same, 4 units away. So what we're looking at here are two particles that have the same sign, they have the same magnitude, and they are the same distance from the point charge. That means that the force pushing this particle to the left is exactly the same as the force pushing the particle on the right. There is going to be no net movement for that particle in the middle. It's just going to be kind of stuck. Let's try the problem up above it. So again, we have a bunch of like charges. The charge on the left-hand side is going to cause that center particle to be pushed to the right because they are the same charge. The charge on the right-hand side is going to cause the center particle to be pushed to the left, again, because they are both positively charged particles. Which one is going to have a greater effect on the motion of the center particle? Well, we have here a significantly greater magnitude of charge. +3 is much larger than +1. In addition to that, the +3 charge is 4 units away, whereas the +1 charge is 5 units away. So what we're dealing with here is, in this situation, we have a greater charge that is closer in distance to that center particle, which means that this situation here is going to have a much stronger effect than whatever forces are experienced on the left-hand side. This is going to have a much stronger effect, which means that this particle is going to be pushed to the left. Now here we have a different scenario because both of the external charges are on the left-hand side of our point charge. We've got this +1 charge pretty far away that is going to repel our center charge. It's going to push it to the right. I don't know why I made that arrow so massively big. And then we have a negative charge because this particle is positively charged and we have this negative charge. That negative charge is actually going to pull these two particles together. The like charges attract each other, or excuse me, the opposite charges attract each other. So again, we're down to figuring out which of these has the greater effect. This charge has a larger magnitude and it is closer in distance to that center charge, which means that the forces experienced between these two charges are much more significant than the forces experienced between these two charges, and that -2 charge is going to attract our center charge and it is going to draw it to the left.